Today we're on chapter 9, quantum weirdness. So Sharon found this. We're all familiar with this.
We're starting.
Psalm says, "When I look at your heavens, the work of your fingers, the moon and the stars that you have established, what are human beings that you are mindful of them, mortals that you care for them?" Where do we fit in the cosmic scheme of things? Well, from this book, What Does God Look Like in the Expanding Universe, I found this little poem, Why Are We Here, by Captain Browning. Why are we here? Deliver us a line about purpose and meaning and the role of humankind. Are we here to have dominion? Are we here to pass a test? Are we here to celebrate the universe in conscious self-awareness? Weave a tale for us, spin a metaphor or two about the grandeur of creation from the quantum point of view. So we've been talking about curveballs. So quantum physics was one curveball for Enns. Quantum physics deals with the very, very small. And some things in there that are pretty weird that challenge our notions of reality. So he said it stretched his imagination, and we're not going to really get into it this chapter, but talking about God, that's next chapter. Hopefully that he'll get into it finally. But we'll get into, we'll kind of hit the edges, touch the edges of it a little bit. So, but first,
Oh, you lost a T.
I lost a T. First, this may be a little bit of a science lesson for quite a bit of this, but bear with me. We're going to go through some of the discoveries of physics and their thinking on our cosmology. Remember 3 or 4 weeks ago, I talked about the ancient cosmology, the dome, and the pillars of the earth and all that, and the stars were fixed in the firmament. Well, a few things have changed since then. So 300 years ago, Isaac Newton revolutionized our understanding of how the universe works with his laws of motion and gravity. And he made some assumptions that space was basically unchanged and things moved through space because of the existence of time, and that was a constant. And then he came up, this is his law of universal gravitation, the formula for it, where the force is proportional, there's a gravitational constant in there, the masses of the two bodies and the distance between them squared, all that. So that was his law of gravitation, which works in planetary scale, but they don't work on the quantum scale. Well, not perfectly, okay, not as exact as something else. So, but they don't work on the quantum scale. So a couple hundred years later, in 1905, Einstein developed his spatial theory of relativity, and 10 years later, his general theory of relativity. The general theory reconciles conflicts between his spatial theory and Newton's law of gravity. So Einstein called the universe a space-time continuum. I kind of like the word fabric because then they talk about it. You interweave the 3 dimensions of space with the dimension of time. Yeah, and time can vary in Einstein's theory. So here's the special theory of relativity equation. Everybody's seen this before, E equals mc squared. Well, I was familiar with that, but I wasn't familiar with his general theory of relativity. And according to him, massive objects like planets and stars create indentations in the space-time fabric. And that's the attraction between bodies that we call the force of gravity. But in his scheme of things, they kind of move towards each other because, to me, I just think of it as it's sloping downhill towards this bigger body, and that's the attraction. It's not force, but so here's the general relativity equation.
And there'll be a test later.
I'd never seen it before. I just wanted you to be and say you'd seen it before. Supposedly behind this, there's a whole bunch of more equations that, like 16 more equations to develop all those different parts of that equation. So it's a little more complicated even than that looks. So
What is a metric tensor?
I don't know tensor math, so don't ask me that.
Yeah.
Sort of second order derivatives, spatial derivatives.
So all I can tell you is this is a differential equation that he had this part of his theory, though, said that a massive body could deflect a light ray. And so in 1919, there was a solar eclipse that gave them a chance to test his theory. And so this kind of depicts that. Here you can see where the star really is, but when you observe it, it's a little bit to the right of there. And so they measured that, and they said it correlated to what he had predicted. So they had verified his theory, at least in that aspect. And they've done other things too, but I thought that was kind of interesting that light bends around, I think the light going in a straight line, bends around a massive body. So his theory of relativity it still works. And so it's reshaped our understanding of the cosmos from what Newton proposed. It's expanded it a lot. And like Newton, Einstein's theory works on cosmic scale, but doesn't work on quantum scale. Quantum scale stuff is weird. That's what Enns says, and what little I know about it, I agree. But on the quantum scale, you're talking about atomic and subatomic size stuff.
Tiny.
Very tiny. So Enns says that the proton and neutrons are about 4 times 10 to the minus. I changed. He had it in, I forget what dimensions he had it in, meters. I think I changed it to inches. But 4 times 10 to the minus 16 inches in diameter. That's a proton size.
That's tiny.
So I can relate to a human hair. Wikipedia said that human hair is about 1,000th of an inch, 10 to the minus 3. That's 2.5 trillion times thicker than a proton. And that's not, a proton's not the smallest subatomic particle. So you're on the very minute scale.
Of course, the concept of size starts to disappear in quantum mechanics.
Yeah.
Okay. No, that's later. It comes up.
Don't confuse us for us.
Well, where did the word quantum mechanics, quantum physics come from? Well, it goes kind of back. What I came up with, and Max Planck had this quantum theory of radiation in 1901. So he talked about energy radiating from a black body in forms of little packets. He called them quantum. And so that's how we got the name of quantum physics from Max Planck. And for light, Einstein called these quantum of energy. He called it a photon. So quantum theory predicts experimental results accurately, but nobody can explain how they can predict them accurately or why the result they get. And here's a new guy, Erwin Schrödinger.
You're going to talk about a cat?
No, I'm not going to get into that one. But we use quantum physics. GPS, MRIs, lasers are a few that are based on it. So I wasn't familiar with this equation, but it's a fundamental equation of quantum physics and named after Schrödinger, who published it in 1926, 100 years ago. one of the most fundamental descriptions we have of nature at short distances. So the equation describes the quantum world behavior in terms of waves, and it gives physicists a handle on the weird world. So just to say, here's, this was one case of Schrodinger's equation. I think this is the one, is this the one that's in the book? I think so. So I put it in there just because he had it in there. But there's two more. The most general form is the one on the left. And then a little simpler form is the one on the right. So you can say you've seen Schrodinger's equation in its most general form and its specific forms. And these are the one. These are these partial differential equations. I don't remember much about differences. You can kind of, on a level of concepts, you know, it's in a, like Newton's law of second motion is F equals ma. Schrodinger's is kind of on that same level of importance, I guess you'd say. That's the quantum counterpart. So if you know a lot of the conditions for a cannonball, you could fire it, you can predict where it's going to be on its path. You can't quite do that with Schrodinger's equation. You can calculate its likelihood of being somewhere in one position or another. So this wave function that captures all the quantum systems myriad possibilities. So there's all these probabilities. This is where it starts getting weird to me. This equation tells you about this wave function over time, as long as you don't look at it, as long as you don't watch it. So we get into this double slit experiment, which was critical to the development of quantum mechanics. And things aren't like you think they are in this double slit experiment. So you create this, you have this device that can shoot electrons at a barrier. It's got a couple slits in it, vertical slits. And on the other side of this barrier, there's a screen that can detect those electrons when each one lands. So what would you expect if you were shooting these electrons through these, at this barrier and there's slits and it can go through? What would you expect to see go up on the other side?
What the slit looks like.
Okay. You would think that each electron would go through the slit, one slit or the other, hit the screen like a pellet, and you'd see, like I said, two bands that correspond to the slits. So you probably already know that, but that's not what happens, of course. Instead, you get this interference pattern on the screen, the detector screen behind it. So it alternates light, dark, light, dark. Well, that's kind of the way waves work. You know, if you think about waves, you can see waves that sometimes they'll amplify. Two waves interfere with each other, they'll amplify or they'll dampen each other out. So that's what makes you suggest you've got a wave pattern. So here's your experiment. And you can see the interference patterns where it gets lighter or darker on the detector screen after you fired them at this barrier. Okay, so that was the first, that was kind of like step one. Well, and so here's another way of looking at it. You can see here's the particles go through and it creates these waves that interfere with each other. And on the screen, you can see these amplifications. We've got a minimum and a maximum. So that kind of is another representation of the interference. Well,
why did they not take into consideration the fact that the slit, whatever that is, piece of wood, piece of metal, that's mass, and mass is gonna change the direction of the flow of the subatomic particles. You'd almost expect that to happen, right?
I wouldn't have, but
The mass is so small that it's probably not significant.
don't get over my head.
Well, and then, then they said the other condition was unobserved, so how do we know if it's unobserved?
Well, they just had the slit there.
No, I'm just saying, without the slit though, they're saying it's when we observe the particles, when we.
Well, we'll get
measure
to
them,
that.
That changes it.
Hang on a second.
Okay. Have me wondering now, Dennis.
Well, anyway, so you fire these electrons one at a time. So how do you get an interference pattern when you only shot one particle or one electron through there? That's what's weird. So somehow this electron acts like a wave, spreads out, going through the slits at the same time, and then it interferes with going through these when it gets on the other side of the slits, and then it collapses back into a single point on the detector screen. That's what I read anyway. So that was kind of, but so the scientists were curious about this. This is so they set up these detectors at each slit so they could see where the electron went through. Did it go through the one on the left or the one on the right? Then they would fire electrons one at a time towards the barrier. So I don't know if this is a trick question or not, but what would you expect to see this time on the detector screen when you fire the electrons one at a time towards this barrier? Now you've got, the only thing you've changed is you put these detectors by each slit.
Now they're not interfering. Right?
Okay, that's what you think you'll see.
That's what the book said.
Okay, so
Think they-
so you know what the book said, so you didn't expect an interference pattern. But since I would have said before I read the book, I would have said, well, I would expect to see an interference pattern. I saw it before, I would see it now. But so that's what I think you might expect. But that's not what happened. As Jane's already said, what they saw was, what was that?
Oh, I said I actually didn't.
Oh, okay. Well, what they actually saw with these detectors at the slits was they saw what we originally thought we'd see, two slots or two bands on the detector screen. Well, okay. So we don't see a wave interference pattern. Now we see two vertical patterns like a particle pattern. Well, what was the difference? Well, all we did was add these detectors to observe the electrons going through the slits. So why would that change the pattern? So
I thought you said that the electrons were fired one at a time.
They were.
At the same time.
They were.
they were.
Okay. That's the part of the experiment that changed it.
No, they were fired one at a time with the wave interference also.
At the same time in the other one.
No.
No, they fired one.
Just at different times. There were multiple electrons, but at different times.
Yeah, one after another. So in the original pattern, they fired one electron and they started seeing a wave interference pattern. So
Everybody does, this just tells me that no matter if you're a particle or a person, everything your behavior changes when you're being observed.
okay. You're ahead of me.
This is on the quantum level.
Yeah.
But everybody, the skills that you do daily, the minute somebody watches you do it, you start forgetting the steps. Wait,
You're saying the electrons are getting nervous because
nothing's watching them.
Well, those are some conjectures we talked about. Jonathan?
I don't think I would carry the analogy that far.
Okay.
Not to the subatomic level?
No,
Okay, Jonathan, were you gonna say something?
not above the sub.
No, okay. When electrons were observed going through the slit, the wave-like pattern disappeared, a particle-like pattern emerged instead. So this is what I think is the weird part. It's like the electrons knew they were being observed. And I don't think an electron is as
Having awareness.
having awareness, I
Yeah.
guess is
Could I interject just a little bit here?
sure.
One of the most, I'm not sure exactly how complete it is of a picture, but imagine what observing means. In this case, if you're, one of the things that is inherent in all of these things is the exclusion principle, or not the exclusion.
The
Well,
uncertainty
anyway,
principle.
forget what the name of it is. Anyway, you can't predict both the direction
The
and the
uncertainty principle.
velocity
Yeah,
of a particle.
yeah.
And one of the reasons for that is in order to do that, you have to hit it with another particle or wave, typically called a wavicle.
Okay.
And so when you hit it with the other wavicle, you disturb what it's doing.
Okay.
So that's what the process of, in that particular case at least, is of observing it. You're actually changing what happens.
With the sensor that they're using.
Yeah.
Oh, the sensor does it.
So the electron has to interact with the, whatever this detector mechanism is.
Yeah.
Has to interact. By doing that,
How does the detector interact with it?
Well, in order to observe something, you have to hit it with another particle.
Well, that happens before you
that's what
observe it,
disturbs
doesn't
it.
it? Doesn't that happen before you observe it?
So
No,
nothing's static.
You're not
Everything
observing
is
it if you don't hit it with something.
energy and emitting energy.
Well, then our eyeballs emit energy that.
No.
They're
You're not observing it with your eyeballs, you're observing the electrons or the photons
Okay.
that result from all of this.
So you're saying the observation can also includes hitting with something.
Yeah, that's one explanation, which seems
Okay.
pretty clear to me.
Isn't this
Less
where
clear to
the
me.
term of Schrodinger's cat in the box came from?
That's
If you
that's
observe something-
another quandary
Yeah.
that we won't
Yeah.
get
But
into.
I'm just saying, if you observe something, then you can identify the condition, whereas if it's unobserved, you don't know.
Right.
Yeah.
There's a question of what, like I said, I don't have Schrodinger cat in this slides, but there's a question, is the cat dead or alive inside?
I'm not sure how good the analogy is, but yeah, basically. You have to observe something in order to know something.
Well, you have to hit a bot. That's a weird.
It just seems weird to me that this electron can be aware that it's being observed. But I'm not a physicist, so that just seems weird.
It isn't the electron, it's the observer.
Okay,
Yeah, the question then becomes, what is the observed?
What does
device-
observed mean?
Well, what does the device emit that would alter the protons or, if
Well, in
it,
this case, I don't know what the detector is,
Okay.
so I would presume electrons.
but if the particle is being observed, it changes its behavior. So
Yeah.
isn't it aware then?
It is, it's aware that it was hit with something.
Going back to what I first said, I think when you put things in the room to monitor it, whether it's human beings or an apparatus of some kind, you have changed the mass within the environment, and we know that mass changes the flow of electrons and protons and all of that, right? As opposed to just shooting something through a vacuum at a screen and there's nothing in between to interfere with it. So I think that's where the observation comes in. The observation is what's changing the behavior. And that's true in all the science. I mean, what April said is absolutely correct. You have human science, it's a little gray sometimes because we have observers and we get nervous about being observed and so forth. But in every aspect of science, even the inanimate, observation changes.
Well, I'm not follow all your argument. The observation changes the behavior. the mass didn't change as far as I know, so I don't see that coming into it, but
But I'm saying, well, how are you measuring the behavior of the, you said you've got a slit and you've got monitors and you've got other things in the room to track the electron
Well,
or proton.
you're getting into details that I don't know about.
Yeah, well, I'm just saying, you changed the environment.
Yeah, it's the existence of the observer itself that changes it, because
Well, I don't know.
it
I-
bends the
okay,
mass of the
Okay,
room.
so based on that, if I'm at a bowling alley
Yeah,
and you're all observing what I'm doing,
yeah.
you can make me have a strike as opposed to a spare.
Yeah.
You can't carry the analogy.
More likely to mix all together.
Yes. Thing is, you can't carry the analogy into
The
the
macro world.
macro world.
No.
You just can't.
Well, I can't answer all these questions, obviously.
Aren't you glad you got this chapter?
I thought it was interesting. The observation changes behaviors, all I can say, based on their experiment. The why, I can't explain. I don't think they can either. So,
I think they probably can.
Mr. Enns has no idea.
Well, you can't say that the subatomic world is separate from the macro world, the visible existence. The two have to interact somehow.
yeah,
We're all made up of subatomic particles.
okay, so,
But, well, I'm just, kind of responding to what Russ said about you can't compare the two. I think the two are intertwined.
well, that's probably where this great theory is supposed to tie the two together has not been developed.
What isn't
Didn't Einstein work on trying to do something like
what
that?
hasn't been developed is where's the region?
Yeah,
What do you do with the region between those two levels of?
Mhm.
yeah, when you
size?
try to marry on the cosmic scale and the quantum scale, how do you do that? And I don't think Einstein and anybody else has come
Well,
up with that.
we don't know that. Yeah, I mean, that's what we're trying to learn.
Yeah,
I mean, we didn't know until 10 or 12 years ago which of these particles provides mass, and then we discovered the Higgs boson particle.
okay.
And we didn't know about that for however many years that humanity's been in existence until just recently.
Until we
Okay.
stand other
So
things
we're learning.
together.
Yeah, the God particle.
Well, I heard the God part. I don't
Okay,
know
that's
what it means.
it's called the Higgs boson particle. It's the particle that gives everything its mass.
Okay, I've heard of it. I don't know anything about it. All I can say is the double slit experiment talks about, demonstrates wave particle duality. And the particle electrons or photons can interfere as waves even when they get sent out one at a time. And the observation or measurement affects the outcome of the experiment, what you see on the detector screen. Okay, so this is what I got out of the book. Somehow the act of measuring, observing disrupts the quantum system, but you can't avoid it, so we don't, it's a big mystery in quantum mechanics. So my question was, what does the experiment say about the universe?
There's a whole lot we don't know still.
Can I put my 2 cents worth in?
Okay.
What does all this mean?
Well, that's the question. I just asked it.
God created science so that humankind would have a challenge to discover it.
Okay, that's pretty good.
So just don't leave God out of all of this.
Well, I'm going to leave that for Jane
God, the creator.
for next week.
Yeah.
Yeah, God comes in next week.
Please God out of this. Tells me that God is just as infinite and complex.
Let's don't let any of this in or doubt in our minds. Okay. We give God the credit.
Well, that's the whole purpose of the book we're studying, is the search for God, for understanding God, and how does God relate to all of this
Okay.
science and stuff.
That's good.
And that God is bigger than what we previously thought
Yeah.
or understood.
And more complex.
Well, okay. The
But
universe,
She does perform miracles.
so this was mine. The universe behaves differently when we watch it. And from Newton's theories, we got the clockwork idea of the universe. everything is going to happen in this particular fashion based on whatever previous conditions existed, that's going to cause certain things to result. But quantum physics is more like a possibility, and your observations enter into that. So that's what I got out of the experiment about the universe, and say what it says about the universe. So I thought, well, if our observations affect the outcomes of things, what if we what does that say about participating? Is this where, I guess, is this where agency comes in? How's that play? You know, some of the things people think there's predetermination, all this. This seems to challenge all that to me. Anybody have a different idea?
So you're
Well, I think-
saying everything's not predetermined.
Well, I don't think so. Did somebody say something?
What you said?
I said everything's not predetermined. Some people would probably argue with that, but I would
I knew
say,
you were gonna say that. It was predetermined.
you know, because I would say there's a whole lot of possibilities out there, apparently.
I think for me, it reinforces the notion that humanity is about mind, body, and spirit. We're not separate entities.
Mhm.
We're not just molecules interacting with each other. There's more to it than that.
Years ago, I had a book, which I cannot find anymore, and I really wish I could. The title was something like Naturalistic Experiments, and basically mathematically expounding on the theory that there are certain things, and maybe many things, where the experimenter becomes part of the experiment. This is sort of what we're talking about on observation.
Right, that sounds.
Okay, that's a good way to put it.
The observer, the experimenter.
Mhm.
Well, there's another aspect of weirdness of quantum physics. Schrodinger, besides the Schrodinger equation, also discovered quantum entanglement, which is weird also. So if you split a photon into two pieces, I guess I'll say them for two, you have these photon twins, they say they're entangled. And they're moving apart from each other because they travel at the speed of light. But no matter how far apart they are, which might be light years away, they're still entangled. Well, what's entangled? What's that mean? That they mirror each other's properties instantly. So even though light travels, we think light travels at a certain fixed speed, whatever, 186,000 some miles per second, and they're light years apart, they can still instantly mirror the other particle, the other twin. And they've done experiments on this.
Not light years apart, but hundreds of meters at least.
Okay, but theoretically they could be
Yeah.
light years apart.
Yeah.
I don't know if how they measured it.
And they're only entangled as long as you don't observe them.
Okay,
They're only entangled when?
As long as you don't observe them.
Did they actually experiment on human twins? I'd like to ask when. If he made that comment that twins, maybe I misunderstood. I did not understand anything of it.
I didn't. Okay, say it again.
Was Mr. Enns talking about human twins knowing?
No.
His twins is what you just put up there.
Yeah.
We're talking about photons.
Photon twins. I just thought we need to ask
Okay.
Lana, who's an identical twin, and her sister lives in Iowa, whether they have something, if they have like some sort of.
Oh, I'm sure they do.
There are things that are odd about twins of way they respond.
Yeah.
There's been articles about one twin does the same, even though they're split apart somehow. They might dress the same way and do some things that are very much alike, even though
My mind went to the human element.
I'm not,
It'd be interesting. if there's
extrapolating
any-
this to humans on this stuff here.
It'd be
Yeah.
interesting if there's any studies of human twins that were separated at birth and then, reunited.
Right.
years later.
Yeah, there are.
There was two brothers that were separated at birth and they ended up growing up. Their names were like really close together.
Ronald and Donald or
Yeah.
something like that.
And they're the same woman.
Yeah.
The women's names were the same and they looked alike.
Yeah, no, there's a handful.
And they dress alike, even though they never met each other until way later.
I'm not clear what his point was here. Is he saying that the two photons, even though they're a big distance apart, are affecting each other, or just because they're the same matter, they behave the same?
They have the same properties, no matter how far
But
apart.
Specifically
they appear to be.
spin.
Yeah, but I mean,
that's
is
a-
that,
That's a common
you're taking
concept.
one photon and splitting it, so it's the same thing.
Yeah.
Okay, it's two halves of the same photon.
Right.
So you'd expect it to behave however. it's
They're a mirror image though.
Actually, they're not, I don't want to get too far into it, but they are separate particles.
Yeah.
They're
Yeah.
created out of nothing.
So
Believe
the
it or
question
not.
was, is he saying that they affect each
But-
other
No,
accordingly, or
they are-
they're just behaving the same? Okay.
What it amounts to is that, as far as I know, is that they're, you can't tell what their properties are unless you observe them. But as soon as you observe one of them, the other one instantly changes to match the first one.
Good, yeah.
So they are affecting each other.
At
Well,
least when we observe them.
Yeah,
But you'd have to observe both of them at the same time to know that.
Okay,
yeah,
Dennis, keep us moving forward here.
yeah.
How do they do this?
no
No
one
one
knows.
knows.
That's what I got out of it. They call it non-locality. Distance doesn't seem to matter to the photon twins. So, according to Enns, some scientists say the distance, and I think this is what Russ maybe said a little bit earlier, the distance doesn't really exist in the quantum world. Because the quantum world is some other kind of realm of existence. That's what some scientists say, according to Enns. But then he mentioned there is a scientist, he's dead now, David Bohm, who said non-locality is not weirdness, but it's reality. And it's reality that's more basic than what we call reality. So we're getting into
What is reality?
what is reality.
Philosophy, I have to say.
So. But Enns liked that. He liked what Bohm had to say, because he said you can't verify it, but he's glad that there are scientists that are interested in bringing physics and philosophy together and asking questions of meaning. So. So one of the questions was, the question isn't whether the archaeology needs to be imagined differently, but how? So how does our thinking about God match the cosmos we inhabit?
You got a lot to learn.
Okay.
Full of mystery.
Okay. Anybody else want? Do you have a clue?
Well, certainly our observations impact, and our experiences impact our belief in God, or our beliefs about God. Everybody has different experiences, and some perceive God as a present spirit, others perceive God in nature,
Mhm.
things.
Okay. David.
That, it might be a fair statement to say that as far as the vast majority people who believe in God, it's kind of Newtonian. It is, this is the clockwork, this is the way it is.
Yeah.
And then there are those of us sitting around this table and others who are digging deeper into what is the spirit, as opposed to just accepting. They get delivered from the Newtonian clock
Mhm.
on Sunday mornings.
Most of us, I think, act and think like we're still in Newton's universe. But trying to go to this, you want to call us the Quantonians? Anyway, trying to transition or whatever from one concept to another concept been difficult. I mean,
One thing that you've mentioned is quantum physics and relativity, and there's never been a theory that combined them.
I think, but didn't Einstein try to do
He
that?
tried,
Wasn't
tried,
that his-
tried, and tried and tried.
Wasn't that his grand theory? He
Yeah.
thought that they should somehow be married together,
And
or,
he never made it.
well, as anybody else knows.
No,
So that's part of that.
most of us don't deal in either the very fast, which has to do with relativity, or the very, very small, which has to do with quantum mechanics.
Right. Yeah.
We deal in
Human size stuff.
in Newtonian size. Yeah.
Yeah, it works for a lot of stuff,
Yeah.
but there's some concepts that it's not really, we're kind of stuck there though. And it kind of limits us in some ways when our conceptions, when we find out the universe is different than what Newton said.
Yeah.
Right, and the universe, I still try to get my head wrapped around what coming back from the Webb telescope and the Hubble and everything, and that they keep saying the universe is expanding. And I'm just thinking, and that must be infinite, right? And it's hard to really grasp that.
And you haven't even covered the multiverses.
Right. I mean, it's so vast. Creation is so vast that
Was that,
I'm just am left speechless.
what was that movie where they said, I don't have time to explain relativity?
Was probably Interstellar.
Interstellar.
Okay.
I thought that was profound.
I don't have time to explain relativity to you. Okay.
Well, somewhere I read a book, and I think I shared this a couple weeks ago, but this professor was giving a lecture on quantum physics, and after the lecture was over, one of the students came up and said something like, "You explained it so well, I understand it." And the professor said, "Then I have to start all over again."
Well, I think this relates very much to theology because there are so many theological concepts that we have developed over time based on experience, revelation, logic, rationale. But at the same time, who can get their mind around heaven? Who can get their mind around a God who is outside of space and time? Who can get their mind around infinite, infinity itself? Who can? And really, our knowledge base is growing, but so are the mysteries. So I do think that keeps us humble, which is a good state to be in.
So you think it's expanding our consciousness or awareness, or whatever the word would be used?
The scientific inquiry, or what are you saying?
Well, all these things you mentioned, the heavens or the,
Well, if they're expanding, then the other things should be expanding too.
or are we still in Newton's universe and it's kind of more limited?
I don't know.
I think they also helps to explain when you view everything as being energetic,
Mm-hmm.
nothing is static. And so it doesn't matter how small or how big, everything is energy. So
Everything's doing something.
everything's doing something.
That solid table is not really solid.
Right. When you
If
get
you
down to
think
the smallest,
Through to that,
whatever.
yeah.
Mhm.
When my students and I talk about that, I have to go back drink my tea quietly.
But then if everything's constantly moving, everything is constantly interacting. So I'm kind of the we are all one theory.
Okay. Well,
Make a good
Enns
song.
says that quantum physics checks out, whether it's weird or not, it checks out. But he says Enns' understanding can't continue as if quantum physics doesn't check out. Most of us don't understand quantum physics, so I'm not sure we can
But it is about energy
enter.
Yeah.
But
and the way everything moves and how it moves. It's either a wave or a particle.
I think as our knowledge about the universe grows, it does demand that we reframe God in some way that allows for that. You know, if we lived 10,000 years ago and we saw the sun go down, we'd say, oh, the dragon ate the sun again, darn it. And then it comes back up the next morning. Oh, great, the dragon spit the sun back out. But,
Right.
you know, now we know about planetary movement and rotation around the sun and all of that kind of stuff. So that would force us to reframe our theological views if it was tied to that. And I think the quantum universe will probably be the same way that we, you know, maybe not in our lifetimes, but as that knowledge grows, people will have to reassess. Okay.
well, do you think?
Not working here.
Do you think that? Okay, I'm gonna take the side of the prehistoric humans. Did they have? Do you think they were more awestruck by what their concept of the universe was than we have been for the last 300 years? And now with quantum mechanics, are we starting to kind of recover some of that awesome awareness?
I think that's very possible. I think the things that we stand in awe of change. And probably, like you say, the sun rising and setting or a volcano going off or an earthquake would be an awesome experience, not in a good way necessarily, but
Yeah.
it would certainly get our attention. But nowadays, it's kind of like 7.6 on the Richter scale over there, and you know, here comes the storm on the weather map, and so I'll go down to my basement now or whatever is happening. We almost take that as a matter of routine. But when we look at something like this, and we're all amazed at, you know, particles jumping around and doing weird things when they're being observed and not being observed, I think that it is kind of awesome.
Well, but, you know, going back to the scripture, you started with the Psalm 8, written by David, we think, somebody. He was in awe even then. You know, I've observed the heavens and the handiwork, and what is humankind that you even know we're here. So I think that sense of wonder has been around for a long time, even though people, you know, 100,000 years ago didn't know what we know now, or people in David's time didn't know what we know now. There was still a wonder at the universe and even being here.
I think anything that makes you feel small is allowing you to stand in the presence of God
Right.
in some way. You know, that amazement.
Is worship having a sense of awe or wonder?
Mm-hmm. For me, it is.
So I guess I'm wondering, will quantum physics help us recover some of that sense of wonder and awe that we lost with Newton's universe?
I have to admit that for those of us who have no chance of understanding this, zero, less than Mr. Enns. He's very humble in the way he talks about it. But I think what might happen for some people is that because I cannot understand it, I want to shut down and
Okay.
I want to just believe all the stuff that I can understand.
Okay.
And maybe that's what Newtonian philosophy is, and that all of us have it to some degree. Because I mean, this is too hard. I don't know how.
Well,
many
or
times
it's
people have
too
said to me,
abstract for
you
some.
know, I can't go that deep. That's
Yeah.
too hard. You know,
Mhm.
it happens in philosophy. It happens in religion.
Mm-hmm.
Clearly, it happens in science.
Mm-hmm.
You know.
So you're talking like certainty there.
Yeah.
But David, you were going to say something. I thought. Were you?
I was just trying to think about how to say it. I'm going to say it not very well. I think while this is interesting, and I think that what Paul says about anything, and also what Ryan was talking about humility, I think that's a really important part. But what if this is just a sideshow and it has absolutely nothing to do about the faith that I have in the spirit of the universe? I don't need to explain it. If I could explain it, if I knew I could explain God, then it wouldn't, he, she, or they would not be God.
Right.
So
I do think though that the value of science, that everything every people that do research, things become more and more measurable. And I think that just adds to the mystery of what we don't know. And so I think the value of that is keeping the awe in it. Because there's always something that we learn, and there's always something else that we don't know yet. And I think that mystery of that is the awesomeness of God energy.
Well, and I think astronauts, we've read about a couple lately, you know, are scientific people, are engineers and have all this knowledge. But those who go up into space really have an experience that transcends just the science or the
Well, at least some.
experiments. At least many of them do. And they come back with this sense of awe, you know, and wonder at all this stuff we've learned, and yet all this stuff we still don't know. There's just some of them are really changed.
Mitchell was one of
It
them.
would be interesting to do an experiment with them to see what their upbringing were.
Right.
You know, because what they maybe had gone through, you know, Christian upbringing or not, how would they have seen that?
Right.
But
I think researchers in any field probably feel that. When something is, you know, whether they're looking for something that gene pool of something or whatever it is, you would feel that awesomeness.
If you get in some of the books about nature, what scientists learn about cooperation in nature between what's above ground and what's below ground, some of that stuff is, to me, is really maybe more explainable possibly, but it seems about as amazing as some of the science space stuff. So, because I had a book, Finding the Mother Tree, which talked about how tree roots cooperate with fungi in the ground, and all this stuff is kind of like, and they more or less through chemical communicate, and it's some of that stuff is, I don't know if it's weird or not, but it's pretty amazing. So that's another story.
But somewhere along the line, it all boils down to quantum
something. Yeah.
all that tree root stuff.
Yeah.
I don't want to get on to another subject. I'm having enough problems with this. But anyway, so this is what Enns says: God is getting bigger. The quantum world is showing us a God who completely transcends our thinking on a level higher, deeper, wider than we could imagine. So I don't know if we need to dwell on this. But think about, how does quantum stuff change your thinking about God, about relationships with other people? And this was, I think, what David was maybe talking about. He said, Enns thought it was good to talk about this stuff and think about it, but don't fall in the trap of thinking that quantum physics explains God. I think I read somewhere somebody said, whatever you say about God, that's not him. Or her.
I have to share an experience that I had a couple of decades ago, maybe 3 decades, I don't know. But one of my former students put together with a colleague, they put together ecology trips to the rainforest. And made me an offer I couldn't refuse.
Mhm.
And so, and I took students, some of my students with me. If they would do this, they would get credit for tropical rainforest ecology. And all they had to do was keep a journal and write a paper.
Mhm.
And they got an A. But anyway, so the highlight of the experience was we went to the Amazon rainforest, and they have this thing called the canopy walkway.
Mhm.
And we did the canopy walkway. And that evening, there was a discussion when most of the folks had gone to their tents, and there were a few of us sitting around the campfire, and somebody said, well, so do you think there's a God?
Mhm.
Mhm.
And there was no debate. That's that.
There's a spirit in the universe somewhere, somehow.
Yeah, you see that diversity. It defies description. So if you got any questions, take a trip to the rainforest.
Well, whatever, the quantum world is part of our universe, weird, however weird it is, and so I have this book here, What Does God Look Like in an Expanding Universe? This guy said, quantum, and you may not agree with this, but quantum physics reminds us that each one of us is a constellation of creative energy, forever fluctuating between wave and particle manifestation. So.
I mean, that's cool.
Yeah.
What do I do with that? It's kind of like Joyce, I think, said earlier that nothing is completely solid. Everything is in flux. The table is solid. The wall is solid. Or no, the table is not solid. The wall is
Not solid.
yeah. How would you describe it? Well, anyway, you know, that may be, but I don't want to run against the wall and see what happens because I have a
But
pretty
you can also affect the energy in and around you,
Mhm.
which is kind of all just
right.
Connected
Except that
somehow.
much of what we know is stationary, like the particle, and much of it is in movement,
Mhm.
including beliefs and concepts and everything else.
Mhm.
Well, it kind of goes back to what we were talking about last week too. It's what we experience that sort of drives, our interpretation of our existence and scripture and everything else. To your point, Ryan, if there's more space between the atoms in a 2x4, that's interesting. But if I get hit with the 2x4 in the head, I'm experiencing the atom. So my experience is say, don't let anybody hit you in the head with a 2x4.
Yeah.
You can't
You are
say,
intimately familiar. Yeah.
And Jesus walked.
and we have to acknowledge that if God is the creator of all, then God is the creator of the subatomic universe as well as the rest of it. So.
Right.
Well, that kind of concludes with this. This was from a previous chapter where Enns said, the universe has brought me to believe more deliberately that God is spirit and is present in every atom and subatomic particle in cosmos, in every person, creature, life form. So is the quantum world bringing us face to face with God as creator? I put the atom and subatomic particles. That's the quantum part.
Mhm. I don't know that we can make that
Conclusion.
I think it can bring us closer to creation, but it's hard to say with certainty that we're coming face to face with God himself or herself, if you wish. We are certainly learning more about the creation,
Mhm.
and which by extension gives us a glimpse of God.
Yeah. Well, even even to say face to face is kind of a metaphor because that kind of puts God with anthropomorphic properties.
Yeah.
But how else do we talk about it? So.
I think a lot of that depends on the person. Frankly, I see more mystery in a universe that's expanding, and I wonder where is it expanding to?
Right.
The quantum, the subatomic level is fascinating to me, but it doesn't bring me closer to God as much as the macro level, what I can sort of see and know. So I think it's individual.
But I do say, you know, what Joyce is talking about, you know, that energy that's in us and all around us. There's something there. There is something to, I mean, we're doing this very simple thing in my family that we are just going and we're sitting with my dad because he's lonely.
Sure.
And we don't talk.
Right.
All you do is you sit there and there's this presence in his house now, you know, that calms him. And so, you know, obviously the love that we have with each other, all of that comes into it, but I do think there is a spiritual presence to all of us. If we can tap into that, we can then share that with each other. That's why, I think that's why we have Community of Christ. You know, the community part of it is very important.
And all this science, when Denny was working on this PowerPoint all week, it reminded me of the phrase in one of the anthems the choir is working on. And it talks about, you know, we do all these things and it's just a tiny glimpse of your glory.
Yeah.
And I thought of that again and again. You know, we're just getting a little bigger peek at the complexity and vastness of all of this that just astounds me. It just,
And I think about this that way too, and not only is it this way astounding, what goes down is equally as astounding, and you know, you can't hold it, but we can share it with that emotion. I can remember at a conference one year, Joan and I were sitting by each other, and all of a sudden we just looked at each other, and it was in the room, and it was in space, and we all were kind of feeling this, and I can't even talk about it most of the time because it's hard to explain it. But
well,
it's a pretty crazy world.
Yeah, it's
And universe.
we don't have it all figured out.
Miniverse.
we can talk more about it next week because we're going to do quantum godness. Jane will lead that discussion.
Great.
Really looking forward to it, Jane.
How do we skip Paul? You know, this quantumness.
He did last chapter.
Maybe you two can collaborate.
No, I can't understand Paul.
I can't understand.
Collaboration if one person can't understand it.
So we're looking forward to Jane opening up fresh ways of understanding God and Jesus next week.
This guy, give him this wavelength.